The promise of knowledge has always been a guiding light for humanity. From the dawn of our species, the thirst to understand the world around us has shaped who we are. When early humans first stood upright and gazed at the stars, it wasn't just out of curiosity. It was a spark that would ignite our destiny. We tamed fire, painted our stories on cave walls, fashioned tools, and carved myths from the unknown. From these humble beginnings, humanity took its first steps toward civilization. But our journey didn't end there. Over hundreds of thousands of years, we evolved, not just physically, but spiritually, culturally, and intellectually. We built empires, sailed uncharted oceans, decoded the laws of nature, and even set foot on other worlds. Yet despite millennia of progress and scientific breakthroughs, some of the universe's most profound questions still remain unanswered. We have discovered how life formed on Earth and even traced humanity's roots back through millions of years of evolution. We know how planets, stars, and galaxies form, and we have pieced together a cosmic history stretching back billions of years. But amidst all this knowledge, one enigma looms larger than the rest, the mystery of when time itself began. In this video, we're diving deep into the story of how modern science is reshaping our understanding of the universe's origins. Before we begin, make sure to hit that subscribe button, give us a like, and ring the notification bell so you won't miss out on the latest cosmic revelations. Let's start at the beginning. For centuries, humans have theorized about how the universe came into existence. Ancient cultures had their own creation stories, be it gods shaping the cosmos from chaos or divine forces speaking reality into existence. While these myths served to explain the unknown, science eventually provided a new narrative. Today, the most widely accepted scientific explanation is the Big Bang theory. First proposed by Belgian priest and astronomer Georges Lemaitre in the 1920s, the Big Bang posits that the universe originated from an infinitely small, hot, and dense point known as a singularity. From this singularity, space itself began to expand, giving birth to everything we see today. Lemaitre's theory gained major support when astronomer Edwin Hubble discovered that galaxies are moving away from us, with more distant galaxies receding at faster rates, a phenomenon now known as Hubble's law. This cosmic expansion, when traced backward, points to a singular beginning roughly 13.8 billion years ago. But it wasn't just the recession of galaxies that cemented the Big Bang's place in cosmology. In 1965, scientists accidentally detected the cosmic microwave background radiation, CMBR, a faint afterglow left over from the early universe, just 380,000 years after the initial explosion. This discovery provided strong evidence that the universe was once much hotter and denser than it is today. For decades, the Big Bang has served as the cornerstone of cosmology. It explained the distribution of galaxies, the abundance of light elements like hydrogen and helium, and the evolution of cosmic structures. But as is often the case with science, new discoveries challenge old models. Fast forward to December 2021, when NASA launched the most advanced and expensive space observatory ever created, the James Webb Space Telescope, JWST. Positioned in a stable orbit over 1.5 million kilometers from Earth, the JWST was designed to look deeper into space and therefore further back in time than any telescope before it. Unlike Hubble, which primarily observes visible and ultraviolet light, JWST specializes in capturing infrared light. This allows it to penetrate cosmic dust and reveal objects previously hidden in the shadows of the early universe. In a way, the JWST acts like a time machine, capturing light that has traveled billions of years to reach us. Astrophysicist Neil deGrasse Tyson put it best: "The farther you look into space, the further back in time you see." Scientists around the world eagerly awaited the telescope's first images. What they didn't expect was that these snapshots would pose serious questions about our fundamental understanding of the cosmos. When the JWST began transmitting its first deep-field images, astronomers were stunned. The telescope revealed galaxies that were smaller, smoother, and older than predicted by the Big Bang model. Not only were these galaxies surprisingly well-formed, but they also appeared in much greater numbers than expected. Let's break this down. If the universe has been expanding for 13.8 billion years, then distant galaxies should appear increasingly stretched and distorted due to cosmic expansion. However, JWST images showed distant galaxies that appeared consistently small, compact, and, most surprisingly, undisturbed. This finding directly contradicts our existing models. According to the standard theory, the early universe should have been chaotic, with galaxies frequently merging, colliding, and leaving behind distorted remnants. Yet JWST captured clean, pristine spiral galaxies, structures that should have taken billions of years to develop. Even more intriguing is the redshift data. Redshift refers to how light stretches as galaxies move away from us, shifting toward the red end of the spectrum. The farther a galaxy, the greater its redshift. JWST detected galaxies with redshifts 2 to 3 times higher than those previously observed by Hubble, suggesting we are looking even closer to the universe's supposed beginning. But these galaxies appear too mature, already fully formed, massive, and stable at a time when, according to the Big Bang theory, the universe was still in its infancy. Additionally, JWST detected at least 100,000 more galaxies in its deep field survey than models had anticipated. This raises a troubling question. How could so many galaxies in such organized states have formed so early? Many cosmologists believe this discovery points to a fundamental gap in our understanding of cosmic evolution. So what are the alternative theories? One possibility gaining renewed interest is the plasma filamentation model. This theory suggests that electric currents and magnetic fields in space interact with plasma, a highly ionized gas, to create vast web-like structures throughout the cosmos. These filaments could have shaped galaxies and cosmic structures without the need for chaotic collisions. In this model, plasma filaments act like cosmic highways, guiding the formation of stars, planets, and galaxies along magnetic currents. This explanation differs from the gravity-dominated model of the Big Bang, proposing instead that electromagnetic forces may play a more significant role on a galactic scale than previously believed. Interestingly, this plasma-based concept isn't new. The electric universe theory, a fringe but persistent hypothesis, suggests that electromagnetic forces, not just gravity, are key drivers of cosmic evolution. While this theory remains highly controversial, JWST's unexpected findings have prompted a few scientists to reconsider elements of it, particularly regarding plasma behavior in space. The implications of such an idea are vast. If plasma filamentation is shaping the universe more actively than we thought, it could explain why we see well-organized galaxies so early in cosmic history. It might also shed light on why large-scale structures, like galactic clusters and superclusters, align along vast cosmic filaments, the so-called cosmic web we've observed. Does this mean the Big Bang theory is wrong? Not necessarily. The Big Bang model remains the most comprehensive explanation for many observed phenomena, including the cosmic microwave background and the abundance of light elements. However, JWST's discoveries suggest that the model may need refining. There could be additional forces or processes shaping the universe alongside gravity and dark matter. Some scientists are now exploring hybrid models where elements of plasma physics, dark matter interactions, and cosmic expansion are all at play simultaneously. At this stage, the universe may be forcing us to rethink some of our most cherished assumptions. So what happens next? Astronomers are continuing to collect and analyze JWST data, hoping to find further evidence that could clarify or complicate the puzzle even more. Future missions, such as the European Space Agency's Euclid Telescope and NASA's Nancy Grace Roman Space Telescope, will also probe the mysteries of cosmic structure, dark energy, and the early universe. For now, humanity stands at the edge of a scientific revolution. We may be witnessing the first cracks in a long-held model, or perhaps the birth of a new way to understand the cosmos. And that brings us back to where we started, with a simple but profound question. When did time truly begin? Let us know what you think in the comments below. Are we close to rewriting the story of the universe? Or are we simply filling in more missing pieces of the cosmic puzzle? Be sure to subscribe and ring the notification bell for more deep dives into the mysteries of our universe. Until next time, stay curious.